My name is Stephan, and I'm going to talk about Android security modules. This is a joint project with my supervisor, Ahmad-Reza, and Adwait, Nadkarni, and William Enck from NC State University. So, as many of you know, over the last years, academia has proposed several very interesting extensions for the Android operating system, which aim to tackle different security and privacy concerns. These are just some of the most well-known examples which aim to tackle different use cases, such as increasing user privacy, improving Android's permission model, or providing better access control on app communication. And these solutions are all very interesting, but they are not really used in the real world. And the main reason for that is that all these extensions require changes to the underlying operating system to integrate enhanced access control mechanisms. So this is the Android operating system stack. On the bottom, we have the Linux kernel, which implements Linux discretionary access control, and in recent Android versions, also mandatory access control using the SE Linux or SE Android mandatory access control framework. On top of that, we have the Android operating system layer, where important security and privacy critical services and data stores, or in Android terms, content providers, are located. And finally, we have applications which are deployed on the device, and they can be divided into pre-deployed system applications or third-party applications which are deployed later on by the user. And as I said before, related work introduces new access control mechanisms into all layers of the operating system. Most of the solutions target the Android operating system layer. Some of the solutions, such as the Flastroid architecture we presented last year here at USENIX Security Symposium, also target the Linux kernel. And there are also solutions which operate on purely on the application layer and introduce so-called inline reference monitors here to improve access control. However, related work has shown that these inline reference monitors are often inadequate because they cannot provide complete mediation, for example, in the presence of native code. So, with all that in mind, we asked ourselves whether it is possible to provide a programmable and generic security architecture on top of which many of these solutions can be instantiated. And to answer this question, we first performed a systematic study of related work in the area of Android security. Now, this is just an excerpt, but what you can see is that while these extensions all have very diverse goals, they actually use very similar security hooks and mechanisms. And one important observation here is that some of these solutions also provide the option to not only allow access or deny access by third-party applications to security or privacy critical data, but also provide fake data back to applications, which is important for privacy concerning use cases. Furthermore, several of these extensions can be extended by third-party hooks. So, with this in mind, I'd like to present to you the overall idea of the Android security modules framework. We provide an access control architecture which is modular and supports multiple stakeholders, such as the user, who's mainly concerned with protecting his own privacy, the platform provider, or the enterprise, who is interested in separating private and enterprise applications and data which are deployed on the device. And in the Android security modules framework, these stakeholders deploy Android security modules, which are essentially Android applications on the device. These Android security modules then interact with the enhanced access control mechanisms we integrated into all layers of the Android operating system. So, to design and implement this architecture, several challenges had to be tackled. First, the Android security modules framework provides fine-grained access control on all abstraction layers of the operating system, and thus has to handle the different semantics and peculiarities of each of these layers. Furthermore, the Android security modules framework preserves existing security invariants on the operating system. And what we mean by that is that ASMs deployed on the platform should only be able to make access control enforcement more restrictive and never overrule denials by the default Android access control mechanisms, such as Android's standard permission model, the discretionary access control model of the Linux kernel, or the mandatory access control model provided by SE Android. Another very important challenge is that our solution must be efficient and only activates our additional access control hooks when they are actually required. That is, when an ASM which is deployed on the platform is actually using them. And finally, since we consider multiple stakeholders which deploy security modules on the platform, a policy reconciliation mechanism is required, which is able to handle decision conflicts between all the different modules which are deployed on the platform. So let me show you the design of the Android security modules platform. On this picture, you see the Android operating system, and in orange, we see the components we introduced. So on the Android operating system layer, we place a component called the ASM bridge. And the ASM bridge serves as a central communication hub between the access control hooks we placed in security and privacy relevant components of the operating system and the individual ASMs we deploy on the platform. On the kernel level, we introduced a patch which allows us to integrate multiple Linux security modules. And this is required because we don't want to allow any Android security modules to allow access to kernel level resources when SE Linux or the discretionary access control model denies access. So when ASMs are deployed on the platform, they first register a callback service with the Android security modules bridge. And this callback service is required to provide communication between the ASMs and the ASM bridge. Once the ASMs are registered on the platform, the ASM bridge queries them for the active hooks. But before it can do so, a reference monitor checks whether the ASMs are actually allowed to be deployed on the platform. This reference monitor in our current implementation is based on Android permissions, but other implementations are feasible as well. So once the ASMs are registered, the active hooks are queries. So only the hooks which are actually required by the ASMs which are deployed on the platform are activated. And yeah, this is good for efficiency. So when at runtime now, an application such as the popular WhatsApp application accesses a security or privacy critical component on the platform, such as the contacts database or the context provider in Android terms, the hook in this component is triggered and a protection event is generated, in this case query contacts, which is forwarded to the ASM bridge. The ASM bridge, in turn, distributes this protection event to all the ASMs which are deployed on the platform. And each of these ASMs can now decide whether it wants to allow access, deny access, or even modify the data which is returned to the WhatsApp application. So for example, an ASM deployed by the user for privacy protection might restrict the WhatsApp application to only be able to access data which it is fundamentally required to access, such as your phone numbers of your contacts and their names. Whereas an enterprise ASM might filter out all enterprise contacts which are stored on the device. Furthermore, we also want third-party applications to be able to make use of our framework. So we provide an API which allows ASM-aware third-party applications to implement hooks which protect their own components and to register these hooks with the ASM bridge so that the ASMs deployed on the platform can provide mediation here. So we implemented our architecture and evaluated it on an LG Nexus 4 device. Our implementation is based on Android 4.4, and there we integrated our ASM extensions and Qualcomm's Linux kernel in version 3.4. This kernel was patched with support for multiple LSM modules, and we deployed our Android security modules LSM here, in addition to the standard SE Linux mandatory access control mechanisms. We evaluated different security and privacy critical aspects, such as operations concerning user interfaces or activities in Android terms, the contacts database, files and sockets. And in our evaluation, we considered the impact of a plain ASM, which always allows access. And the reason for that is that we are mainly interested in the performance impact and the energy consumption impact of the overall framework and not of the individual ASM. In an automated test suite, we evaluated the performance overhead introduced by our framework, as well as the power consumption overhead, which we measured using Qualcomm's Stephan profiler. So these are the results for the performance evaluation. This is just an excerpt. In the paper you can find a much bigger evaluation. We performed different operations such as starting activities, querying the context database, reading files, and connecting sockets. And all these tests were performed 50 times to come up with these average values. And in blue we see the baseline measurements on Android 4.4. In red, we see the results for the ASM framework with no ASM deployed on the platform, and in green, we see the results for the plain ASM I talked about before. So what we can immediately see here is that the impact regarding performance when no ASM is deployed on the platform is minimal. And overall, we see that the overall performance impact will not be noticeable by the user, according to the absolute numbers. We further performed several power consumption measurements in a similar experiment. And again, we see that compared to the stock Android operating system, the power consumption overhead introduced by the ASM framework is minimal, especially when no ASM is deployed on the platform. So let me show you an example use case. We've seen the use case for privacy protection with WhatsApp before, and in the paper we discuss several other use cases, but I think this one here is much more interesting. At AGR CCS this year, we presented a paper which proposed the ConXSense architecture, and this architecture provides context-aware access control on the Android operating system. What we mean by that is that we use environmental information, such as nearby devices, which are sensed via Bluetooth or Wi-Fi, location information, or the user interaction with the device, to derive whether a device is currently used in a safe or unsafe context. And depending on this information, we enforce access control rules for untrusted applications on the platform, such as applications accessing the GPS or the camera, or sensitive information stored on the device. And to implement this solution as an ASM, we just took the original logic from ConXSense and introduced a ConXSense ASM, which registers an ASM callback service with the ASM bridge. And using this callback service, it communicates with the different components deployed on the platform, such as the activity manager service, which is responsible for application interaction, the location manager service, which provides access control for location information, system content providers, and the camera service. And this took us merely a few hours because we already had the original logic, and an ASM, as I said before, is just an Android application. So the implementation was quite straightforward. So with this, I'd like to conclude my talk by saying that, as we have seen, ASM greatly simplifies the implementation of use case-specific security solutions. When developers adopt the ASM framework, they do not need to worry about the access control enforcement anymore, but can rather concentrate on implementing the actual decision logic in their ASMs. We are currently working on extending the Android security modules framework for further use cases and implementing these on top of the ASM framework, such as dual persona phones, where we separate enterprise and private data and applications deployed on devices, or dynamic application behavior analysis, where we use the Android security modules framework to profile applications and their use of security and privacy critical components. This information could, for example, be useful for malware analysis. Furthermore, we are working on porting the ASM framework to new Android versions, such as the upcoming Android L version. And we're actively working on pushing the ASM framework to device vendors and ideally the Android open source project. So I'd like to end my talk by inviting you all to check out our website, androidsecuritymodules.org. where you can find an open source implementation of our framework, which you can freely use for non-commercial and academic purposes. So thank you, and I think we have some time left for questions.
Thank you, Stephan. We do indeed. As you know, there's a mic over here. I'll bring one over there if anybody wants it. And please state your name and affiliation for the benefit of the scribes who are taking notes.
Sure. Indranil Banerjee from Qualcomm. Thanks for a great talk. Could you talk a bit more about what happens when there are conflicts in policies between, say, the user ASM and the enterprise ASM?
Yeah, thanks for the question. Very interesting. We have discussed this in the paper a bit. Currently, we use a consensus strategy here. So the ASM bridge consolidates all the access control decisions by the different ASMs deployed on the platform. And if a consensus can be reached, that is, as long as not one ASM denies, the access is allowed. But certain other implementations are feasible, of course, as well, such as a majority vote, for example, or a hierarchy of ASMs.
Thank you. I bring this up because I guess as an attacker, my first move would be to deploy a malicious ASM which just says that everything is allowed.
Yeah, this is also something which we discuss in the paper. So in the end, the question is how the deployment model for ASMs is. So yeah, ASMs are very privileged components, and we have a reference monitor in place to control which ASMs are deployed. But how this reference monitor implementation exactly looks like, we can, I guess, debate over that offline after the talk, because this might get very technical.
Yeah, thank you.
Hi, Manuel Egele, Boston University. So one thing that is kind of concerning in the current Android as it is deployed is that the principle for the access control is an individual application. However, oftentimes it's the case that an application, the application logic, has a legitimate need to access some privacy-sensitive information, let's say your location information. Yep. The problem being with having third-party libraries in the same principle, everybody gets the same access rights. So I was wondering whether in your framework you have a concept of further distilling the application into its individual constituent components.
This is a very interesting question, and actually I had a rather lively discussion about this yesterday. As you said, in the current implementation, applications are basically sandboxed as one. All components in the application are running in the same sandbox. So the ASM framework currently does not provide the ability to separate these components. We can enforce access control based on the process ID of an application, and components in Android can be separated in different processes, but this is not the usual way how Android applications are developed. But yeah, if you like, we can talk about that offline, because this is, I think, a very interesting area of research at the moment.
Absolutely, come and find it. Thanks.
Any other questions? If not, let's thank Stephan again.